My name is Alvaro, and in this video I will be solving the two-sum question in Leetcode in this series, in which I will attempt to solve every single problem in the famous blind post that has 75 Leetcode questions. So this is the first problem since it's the simplest one, so let's read it. It's called two-sum, and I will leave the link of the problem in the description, of course, so that you can try it yourself. Given an array of integers nums and an integer target, return indices of the two numbers such that they add up to target. You may assume that each input would have exactly one solution, and you may not use the same element twice. You can return the answer in any order. Example 1. So we have the input array nums, which is 2, 7, 11, 15, and target 9. So we return 0 and 1 because the 0th and the 1th element add up to 9. Pretty straightforward. Same with here. The 1th and the 2th add up to 6. And I'm saying it that way because I don't like saying first when the first is 0. I don't know. That's just kind of like a thing for me, but and then here 3 plus 3 is 6, so we'll return the 0 and the 1 index. Okay, and there exists a valid answer, and it's only 1. Okay, so it says follow. Can you come up with an algorithm that is less than O of n squared time complexity? Yeah, so the first solution that I'm thinking about, and we can code it up, will be the naive solution. It will go something like this. So we start at here, for example, we would start at 2, and we would compare 2 with every other number. And if it adds up, if the two numbers add up to the target, then we'll return the indices. So suppose that we have target 26 instead of 9. So we would have 2 plus 7 doesn't add up, 2 plus 11 doesn't add up, 2 plus 15 doesn't add up, and then 7 we compare with 11, and we start comparing with 11 because we have already compared 2 and 7 when we've used comparing the 2's. Then we add up 7 and 15, and we see that that doesn't add up. And then 11 plus 15 adds up, so that's 26. That's the target that we wanted in this hypothetical case, of course. And then we will return 2 and 3. And this is, of course, as you can see, an O of n squared algorithm, because here we do n comparisons, then we do n minus 1, n minus 2, n minus 3, and so on and so on. So if we add up all those together, it ends up being O of n squared, because we do more or less O of n operations in O of n times. So this naive solution would look something like this. So we would start at index 0, let's say. We can say for I in range, I don't even think we need to type idx 0. So we can say for I in range length of nums. So we start in here, and then we say for j in range I plus 1 length of nums, if nums of I plus nums sub j is equal to target, then we return, we're supposed to return a list, it looks like. Yep, and the output is a list. So we will return this. You can run the code. And as you can see, it's faster only than 34.12% of the solutions, because it's an O of n squared algorithm. Obviously, if we run it again, it might be a little bit up, a little bit down, but the main idea is that it's not the most efficient solution, as you can see. So we can think of another solution for this. You can say the more efficient one. So let's say, for example, we have 2, right? If we find a 2, then let's say if we found a 2 right in the beginning, sorry for repeating myself. Actually, let's go again with the example. Let's make the target 13 now. How about that? So suppose that we have a 2. And we want to make our target 13. Um, okay, so suppose that we want to make our target 13. So obviously, if we find a 2 and we know that our target is 13, then what we want is we want to find an 11, right? Because 2 plus 11 adds up to 13. Meaning that if we are at the current number and we already know the target, because the target, remember, is given to us, then we want to find the number target minus the current number. Let me repeat. I am at 2 right now. That's the current number. The target is 13. Therefore, the number that adds up to 13, if we add up 2 to it, is target minus the current number. So what we can do is we can traverse the list, and what we can say, we can use some sort of data structure that allows us to store elements and also fetch them in instant time, in O of 1 time, because otherwise it will be inefficient. In this case, we will use a hash set. So what we can say is, okay, we initialize an empty set. We can call them found or seen. Let's call them seen. So as we traverse the elements, so we can say for I in range length of nums. And actually, now that I think about it, since we're returning the indices, what we can do is we can, instead of using a hash set, we can use a hash map. And what we will do is we will make the numbers themselves the keys, and then we will make the indices the values associated with those keys. And the algorithm will run as follows. We encounter an element in the list. Remember, we are trying to find the number that is target minus the current number. So if the target minus the current number is a key in the hash map, and we can check that in O of 1 time, if it exists, then we can simply return the value associated with that key and the index of this current number, because those numbers add up to target. If that does not happen, however, what we can do is we can store this number as a key in the hash map and the index as its corresponding value. And this should return us the proper output. So for I in range length of sums, as I said before, we initialize an empty hash map. And what we can say is, obviously, this is going to be slightly more inefficient than another solution, but I'm just going to write it down for clarity. We can say is, actually, ignore what I just said. So we can say if target minus nums sub I in seen. So remember, if we have already seen this number, that means that we have found, in this case, at this point, if we're at 11, right, it means that if 2 is in the hash set, which it is, then we can simply return the current number, and, well, we can, technically, I guess what we're going to do is we're going to return the previous number, so we can say return seen sub target nums I. So this will be the index associated with the key corresponding to that value, and then the current index. And the reason why I'm returning this one first is because obviously every index that we've visited is stored in the hash map. So this index will always be smaller than I. And it seems, I'm not entirely sure since it doesn't specify here. Oh, it says you can return the answer in any order. Okay, I guess you can return them both, like either this way or flipped. It doesn't really matter. So if the target, if the number that we want that adds up to target plus the current number, if the number that we want to find such that the current number plus that number adds up to target is in the hash map, then we return the indices corresponding to them. And if not, then what we can do is we can say, okay, well, I'm just going to store the value for whenever I encounter another number that we actually that actually meets this condition. So we can say, okay, the current number is num sub I. So that will be the key. And then we can say we can set the index as I. And this should work. And this runs faster than 71.59% of the solutions because it's an O of n. It uses O of n time complexity and O of n space complexity. The reason why it uses O of n time complexity is because it traverses the array, and whenever you store in a hash map, it's an O of 1 operation, and whenever you look up something on a hash map, it's an O of 1 operation as well. Therefore, we do O of 1 operations n times in the worst case scenario. So it's O of n time complexity. And the reason why it's O of n space complexity is because in the worst case scenario, we're going to store O of n elements, meaning pretty much all of the elements except one, n minus 1, which is big O of n. Therefore, this solution uses O of n time complexity, like I said before, and O of n space complexity. Hope this helps, everyone. I hope you enjoyed the video, and we'll be here for the next one. Bye-bye.